Hello, Math 1224. This is Dr. P with Lesson Launch 501, Divide and Conquer. So take a look at the integral I've written here in purple. I've recently discovered how to make colors other than red and blue on this thing, so I'm going to be getting pretty adventurous with the color scheme here. If you watched the last video, Lesson Launch 404, you might think this is a prime candidate for the method of partial fractions because we can rewrite the integrand as x squared minus 3 over x plus 4 times x plus 4 dx. And you might go ahead and set out to rewrite. Let's change colors here. There we go. You might ask yourself, could we write x squared minus 3 over x plus 4 in the form a over x plus 4, that's the first factor, plus b over x plus 4. You might ask whether there are constants, a and b, for which those two functions are exactly the same. Well, if we add the two functions, or add the two fractions on the right, we get, now you'll notice these denominators here, these two, they're exactly the same. So if I add these two fractions together, I'm just going to get a plus b over x plus 4. And the numerator of that function there, I'm trying to pull up the highlighting tool, see if I can use that. That's nice. That numerator is a constant. So if we try to link this function here to this one, no, I didn't want to highlight that. I wanted to just draw a line there. There we go. We try to link that function to this one. There's no way those are going to be exactly the same function because this one here has a quadratic in the denominator, which we can't get rid of, and this one has only a linear x plus 4 in the denominator. So those are not going to be exactly the same function. So the moral is, this partial fraction decomposition here, this one, it's not going to be a viable partial fraction decomposition for this function, which makes me sad. Alright, so the question is there any other technique or strategy that we can use to integrate that function that we started out with there, x squared minus 3 over x plus 4 times x plus 4? And it turns out that there is actually a way to do this using partial fractions, but we have to change the decomposition a bit. So I'm going to move down here. Oh, excuse me. There we go. And we're going to try again. All right, I'm going to try green this time. So the question is, can we come up with some useful way of rewriting this function here? And it turns out there actually is a way to do this, but there are two things that we have to address. There's two problems here. Two problems. Number one is that the degree of the numerator is bigger than or equal to the degree of the denominator. In other words, if I look at the numerator here, that's degree 2. Denominator is also degree 2, which means any conventional partial fractions approach I might want to take is not going to work. It's not going to give us something equivalent to x squared minus 3 over x plus 4 times x plus 4. That's something I'm going to have to deal with before I can deal with the partial fractions part. And then the other part is the factors in the denominator are the same. And you might have noticed how that came into play up here when we were trying to do a partial fraction decomposition on this function here. When I wrote my partial fractions, they both had the same denominator. So when I added these two things up, I got a rational function whose denominator was just x plus 4. There was no x plus 4 squared down there, and there's nothing I could have done that would have given me an x plus 4 squared that couldn't be reduced down to this. So this partial fraction decomposition just doesn't capture the entire complexity here when the factors in the denominator are exactly the same. So the way that we're going to address these problems, there's really two things we're going to do. We're going to address problem number one first by using polynomial division, which might be something that you need to review. I'm probably not going to do a complete review here, but there are other places like Khan Academy where you can find a more thorough explanation of how to do polynomial division. I'm just going to do a quick demo here. And then once we've done that, number two, to deal with the factors in the denominator exactly the same. Now that's not something I'm going to be able to change by making just cosmetic changes to how the function's written. Those are always going to be the same. So instead, I'm going to try a different partial fraction decomposition. But let's do number one first. All right, so I'm just going to zoom out here. All right, so number one, I want to find a different way of rewriting x squared minus 3 over x plus 4 times x plus 4. So to do that, I'm actually going to do the polynomial division, x squared minus 3. And just as a reminder, when we're doing polynomial division, it's usually best to have at least a placeholder for each term, even if that term has a coefficient of 0. That's why I'm putting that 0x there. And we're going to divide by x squared plus 8x plus 16. Easier to do this with that in unfactored form. All right. Now I feel like I've not left myself quite enough room here. Let's see if I can move that. There we go. Sometimes my tablet doesn't cooperate with me when I want to do that. Okay. So to divide, we're going to look at the lead term here and the lead term here and see that this goes into this one time. And then 1 times this is x squared plus 8x plus 16. And subtracting gives us negative 8x. These two, of course, cancel out. 0x minus 8x is minus 8x. Negative 3 minus 16 is negative 19. So this tells me that I have a quotient of 1 and a remainder of negative 8x minus 19. And the crucial part here is how to rewrite my original function given that information. So what this tells us is that x squared minus 3 over x squared plus 8x plus 16 is 1, the quotient, plus negative 8x minus 19 over x squared plus 8x plus 16. And then I'm going to rewrite that as 1 plus negative 8x minus 19 over x plus 4 squared. And now for the partial fraction decomposition part. So I'd like to rewrite this part here using partial fractions. But the decomposition I use has to be a little bit different. When the denominator has a duplicate factor like x plus 4 squared, I have to use the decomposition a over x plus 4 plus b over x plus 4 quantity squared. And it turns out that will give us a rational function that's equivalent to this if I pick the right constants a and b. All right, so now the technique is pretty much the same as before. I'm going to multiply through by the denominator x plus 4 squared and try and find the right constants a and b. So multiplying through by x plus 4 squared, I get negative 8x minus 19 equals a times, okay, and then I have an x plus 4 because I know that one of those factors is going to cancel out here, but I'm still going to have one factor of x plus 4 plus b, because both of these factors get canceled out by that multiplication. All right, so I got negative 8x minus 19 equals ax plus 4a plus b. And I look at that, that's a linear polynomial in x, and it's got a linear term, which is ax, and a constant term, which is 4a plus b. And it turns out the algebra on this is actually a little bit easier than the algebra I did in the last example in the previous video, because you'll notice this is the only linear term I have over here, ax, and this is the only linear term I have over here. That means that a has to be equal to -8, and that's that. Now I also know that 4a plus b needs to be equal to -19. So 4a plus b is equal to -19. But I already know that a is -8, so that tells me -32 plus b equals -19, which I believe is going to make b equal to 13 if I've done the arithmetic correctly. So I think, and this is a very tentative I think, because I've discovered it's a lot easier for me to make a mistake when I'm doing one of these recordings and I'm a little nervous than when I'm in class or when I'm just doing work for myself on paper. But anyway, I think this means x squared minus 3 over x squared plus 8x plus 16 is going to be equal to 1, that's that 1 that I had earlier, plus, and then I'm going to have that -8x minus 19 over x plus 4 squared part. That is -8, that's my a, over x plus 4 plus -19 over x plus 4 squared. All right, let's just zoom out and kind of get a big picture view here. There we go. All right, so that's what's going on here. Just to summarize, I rewrote this as 1 plus a fraction where the degree of the numerator was less than the degree of the denominator. That part's essential. Partial fractions won't work unless you have that. And then once I did that, I decomposed this part using partial fractions, and I had to use a special partial fraction decomposition there because of the repeated factor in the denominator. And then once I had the right constants, -8 and 13, sorry, and I already see I made a mistake here. I've chosen the wrong factor there. So let me see if I can get rid of that. Yeah, I have to apologize. I don't think this thing has a working eraser tool. It's annoying as heck because I'd like for it to be easier for me to correct mistakes. So I'm just going to have to scratch this out here. That was bad. B was equal to 13. That should be a 13 there. Okay, my apologies for that. But anyway, now I haven't finished the problem yet. I was trying to integrate all of this. I wasn't just trying to write it in a different form. I wanted to be able to integrate. And the beauty of this process, is, as gnarly as it is at times, is that this does turn this function here, this function, into something that I do know how to integrate. I know how to integrate 1. I know how to integrate something over x plus 4, as long as that something's a constant, and I know how to integrate a constant over x plus 4 squared. So I think at this point I can complete the process. Integral x squared minus 3 over x squared plus 8x plus 16 dx equals the integral of 1 dx plus the integral of -8 over x plus 4 dx. Need a little bit more room here. Plus the integral of 13 over x plus 4 squared dx. And that's going to give me, well, the integral of 1 is just x. And then the integral of this is going to be, let's see, that's minus 8 natural log of x plus 4. And then finally, the integral of this, that's going to be, you're going to have to check me on this, but that's going to be negative 13 times x plus 4 to the minus 1. So negative 13 over x plus 4 plus c, I think is what I'm going to get. So there you have it. That's a heck of a lot of work for that result, but there we go. But I think that's what the antiderivative of x squared minus 3 over x squared plus 8x plus 16 is. Feel free to check for yourself using Wolfram Alpha or something. But anyway, that is a more advanced example of how to use partial fractions. And now you have most of the techniques that you need to be able to solve a partial fraction problem. I'll probably cover one other little wrinkle in class. But for now, that's it. Thank you.